Welcome to the deep dive. Today we're cutting straight through some of the complexity in classical mechanics and electricity. We want to find that single, universal mathematical thread that connects them all, the linear system.
That's right.
Our mission is to take a close look at Chapter 25 of the Feynman Lectures on Physics.
Oh.
Now, this chapter is kind of a genius move because it doesn't really introduce brand new physics concepts.
No, it doesn't. It's more of a synthesis.
Exactly. It takes things you probably already know about, like springs, damping, circuits, and it shows how they're all governed by just, well, two ridiculously simple algebraic rules.
And that's the real power here. Feynman's basically arguing that understanding linearity is the shortcut. It's the key to unlocking huge areas of physics.
So if a system is linear, we know exactly how it's going to behave. Doesn't matter if it's a pendulum swinging or a radio antenna picking up signals.
Precisely. The underlying math is the same.
Okay, let's get into it, starting with the map itself. We're talking about that big differential equation, the one that describes the driven, damped oscillator. The one.
Oh, yeah, the classic physics beast.
Right. But instead of just reading out the symbols, let's focus on the structure. It's basically an equation where you get terms related to acceleration, velocity, that's the damping part, and position, like the spring force,
And they all add up on one side.
to equal the external driving force on the other side, the F of t.
Exactly. And Feynman introduces this really neat shorthand. We can sort of bundle up that whole left side, all the operations happening to the system, like derivatives and multiplications, into a single symbol, the L operator.
So Lx just represents all that internal physics stuff happening.
Right. And the crucial question is, what makes that operator L truly linear? It boils down to two fundamental properties. These are like the dividing line between physics problems we can really handle nicely and, well, chaos.
Okay, what are they?
So the first one is called additivity. It means if you operate on the sum of two different responses, say x and y, so Lx plus y, you get exactly the same result as if you operated on x and y separately and then added the results, so Lx plus Ly.
No extra weird interactions popping up just because
Okay.
you added things together.
Exactly. The
Yeah.
system doesn't create new cross terms. And the second property is homogeneity.
Okay.
This just means if you scale up the input by some constant factor, let's call it a, so you look at Lx, the output scales up by that exact same factor. It just equals a times Lx. Simple scaling.
Wow. So just those two rules, simple addition and simple scaling. That's it. That determines if a physical problem fits into this whole powerful linear framework.
That's the definition. If those two properties hold, you've basically unlocked this massive toolkit for solving the problem.
Okay, so if the system is linear, let's look at how we actually solve the equation Lxt, where Ft is that external force driving things. Why does the solution always seem to come in two distinct pieces?
Yeah, that structure is non-negotiable, really, for linear systems. You always get two parts. Part one is what Feynman calls the free oscillation. Let's call it x sub 1.
Okay.
This solves the equation Lx equals 0. It's how the system would move if you just, gave it a nudge and then left it completely alone, no driving force.
And the second part.
The second part is the forced oscillation. Let's call it x sub 2. Now, this is any particular solution you can find that satisfies the full equation, Lx FAFT. It's the system's direct reaction to that ongoing external force.
Yeah, and the total motion, the actual physical response we see, is just the sum of those two. X equal 1 plus by 2.
Just add them up. That's the general solution.
Okay. But you often hear the free oscillation part, the guy by one, called the transient solution, right? Especially if there's any friction or damping involved.
Yeah,
Because it eventually dies out.
that's right. It usually does.
So if it just disappears after a while, why do we even need to bother solving for it?
Yeah.
Doesn't the forced solution, the by two part, kind of take over and become the only thing that matters in the long run?
That's a really good question, and it gets right to the heart of initial conditions. You're right. By one is often short-lived if there's damping, but it's absolutely essential because it's the part that lets us account for how the motion started.
Wow. Okay.
You see, the free oscillation equation, Lx, 0, for a second-order system like our oscillator, needs two independent parameters, two constants, to define its general solution.
Like an amplitude and a phase, maybe?
Exactly, or maybe the initial position and initial velocity. Those two constants are precisely what we need to match the specific way the system was set in motion at time t0. So while the long-term behavior might be dominated by the forcing term, Ft, that initial transition period, that's entirely down to the transient motion by one.
Got it. So it bridges the gap between the starting conditions and the eventual steady state driven by the force.
You've got it.
Okay, so if that's how we find the pieces of the solution, let's talk about how they interact. This brings us to maybe the most crucial concept in the whole chapter, superposition.
Yes, superposition. It's really just a direct consequence of those two linearity properties we talked about, additivity and homogeneity.
How so?
Well, it means that if you have, say, two different forces acting on the system at the same time, let's call them Phi and Fib, the total response of the system is simply, well, it's just the response you'd get from Phi acting alone, added to the response you'd get from Phi acting alone.
So x total equals, say, plus f xb, simple addition again.
Simple addition. And this isn't just some mathematical curiosity. It's absolutely fundamental to how huge parts of physics work. Think about electrostatics, for instance.
Okay.
The electric field at any point in space due to, I don't know, 1,000 different charges scattered around, it's just the vector sum of the little electric field contribution from each individual charge. You just add them up.
No complicated interactions between the fields themselves.
Nope. Just simple vector addition. And that linearity is precisely why we can even solve something as complex as Maxwell's equations, which govern all of electricity and magnetism.
That makes sense. What about a more, maybe, everyday example? Feynman uses radio tuning.
Ah, yes, the radio. Perfect example. Imagine your radio antenna. It's constantly being bombarded by electromagnetic waves from, well, dozens of different radio stations, right?
A whole jumble of frequencies.
So that total incoming signal, that's your driving force, FT.
Yeah.
It's actually the sum of signals from, say, a station at 780 kilohertz, another at 550 kilohertz, and maybe many others.
Okay, so the FT is already a sum of forces, Phi plus Fb plus Fab.
Exactly. And because the electrons inside the radio behave to a very good approximation as a linear system, the total electrical response inside the radio, the currents and voltages, is just the sum of how it would respond to the 780 kilohertz signal alone, plus how it responds to the 550 kilohertz signal alone, and so on.
But then how do we tune into just one station? If the radio responds to everything, wouldn't it be just noise?
Ah, that's where the design of the linear system comes in. The radio circuit is specifically built to have a very, very sensitive response curve. You have to imagine this curve, plotting how strongly the radio responds versus the incoming frequency.
And it's sharply peaked.
Extremely sharply peaked, ideally. Right at the frequency you've tuned the dial to, say, 780 kilohertz. So even though the radio is responding a tiny bit to the 550 kilohertz signal, its response at 780 kilohertz is maybe thousands of times stronger.
And that sharpness, that peakiness of the response curve, that must be related to the damping or friction in the system, right? Like we discussed with the transient solution dying out.
Absolutely. It's directly related. Less damping, or in electrical terms, less resistance, leads to a sharper, higher peak. We actually have a term for this sharpness. It's called the Q factor, or quality factor.
Q factor, okay.
A high Q means low damping and a very sharp selective tuning curve. It's exactly what you need to pick out one station from all the others crowded onto the airwaves.
So low friction, high Q, sharp tuning, high friction.
Things low Q, and the response curve gets broader and flatter. The radio would be much less selective, picking up interference from nearby stations.
This ability to break down complex inputs and add up simple responses, it feels like it opens the door to some powerful mathematical tricks. Feynman mentions Fourier analysis.
Oh, it's more than a trick. It's a cornerstone of physics and engineering. Fourier analysis is basically built on superposition. It tells us that any complicated, messy driving force, FT, imagine some really jagged curve, like in Feynman's figure 25-4, or even a sudden sharp impulse can be thought of as just the sum of many, many simple sine waves of different frequencies and amplitudes.
Okay, like building a complex sound out of pure musical notes.
Exactly like that. And because the system is linear, we can figure out how the system responds to each individual sine wave component, which is usually a much easier problem to solve.
And then,
Thanks to superposition, you just add up all those individual sine wave responses to get the total response to the original complicated force. It turns a potentially horrible calculus problem into just addition.
That's incredibly powerful. You also mentioned something about an impulse response, a Green's function.
Yes, that's kind of the limiting case of Fourier analysis in a way. Imagine breaking down that complicated force not into smooth sine waves, but into a series of incredibly short, sharp kicks or impulses. like tapping the system instantaneously over and over again with varying strengths.
Okay, like a series of tiny hammer blows making up the overall force.
Precisely. Now, if you can figure out how your linear system responds to just one single standard strength kick that's called the impulse response or the Green's function, then you can find the response to any arbitrary force Ft.
Wow.
You just add up or technically integrate the responses to all those tiny kicks that make up the force Ft, scaling each response by the strength of its corresponding kick. Again, linearity lets us build up the complex solution from simple, known building blocks.
It really seems like linearity is the key to making complex problems manageable.
It absolutely is.
Let's circle back a bit to the simple oscillations themselves, section 25.3. We talked about damping making the transient solution die out. How exactly does that decay happen?
Right, the effect of damping. If we assume the standard type of friction, where the frictional force is proportional to the velocity, which is a pretty good model for many real-world systems like air resistance at low speeds or dashpots,
Okay.
then it causes the amplitude of the free oscillations to decrease over time. But it's not a linear decrease, it decreases exponentially,
Exponential meaning.
meaning the amplitude A at time t is given by the initial amplitude A0 multiplied by e raised to the power of negative gamma t, where gamma is related to the strength of the friction. A equals A0e,
Right.
gamma.
So it drops faster at the beginning when the amplitude is large, and then the rate of decrease slows down as the amplitude gets smaller.
Exactly. Another way to think about it is that the percentage decrease in amplitude during each cycle of oscillation remains constant, even as the overall size shrinks.
And understanding this exponential decay is important for understanding resonance, isn't it? Why does the system seem to prefer being driven at its natural frequency? Why does it absorb energy so much more efficiently right at that specific frequency, omega 0?
Yeah, it all comes down to timing and phase. Think about pushing someone on a swing, our classic mechanical oscillator example.
Right.
If you time your pushes perfectly, giving a little shove forward just as the swing reaches the back of its arc and starts moving forward again, that is. You push at the natural resonant frequency. Then every single push you give adds energy to the swing effectively. The amplitude builds up.
Makes sense.
But now, what if you try to push slightly off frequency? Maybe a little too early or a little too late compared to the swing's natural rhythm. Sometimes your push will still add energy, but other times you'll actually be pushing against the motion, effectively removing energy or canceling out some of the work you did earlier.
So the energy transfer becomes really inefficient if you're not in sync.
Drastically inefficient. Only when the driving force frequency perfectly matches the system's natural frequency, omega, do you get that constructive interference on every cycle, allowing the system to absorb energy continuously and build up a large amplitude response. That's resonance.
And we can visualize this with that resonance curve we talked about with the radio tuning. Feynman has figure 25-5 showing this.
Exactly. That curve plots the amplitude of the forced oscillation, the by 2 part, against the frequency of the driving force. And what you see is a peak right at the natural frequency, omega.
And the height and sharpness of that peak depend
on the damping, or friction, represented by gamma. Just like with the radio's Q factor. If you have very low friction, low gamma, high Q, the peak is incredibly tall and needle sharp. The system responds hugely, but only in a very narrow range of frequencies around omega.
And if you have high friction,
high gamma, low Q, smears the whole thing out. The peak becomes much lower, broader, and kind of rounded off. The system still responds most strongly near omega, but the response is much weaker overall, and it responds noticeably over a wider range of frequencies. The width of that resonance curve is actually a really good measure of the damping in the system.
wow. Okay, so the math connects damping, Q factor, resonance width, radio tuning sharpness.
Yeah.
It's all tied together.
It really is. And what's perhaps even more fascinating, and this is section 25.4, is the universality of this exact mathematical structure. We've been talking mostly about mechanics, springs, masses, friction, but the same equation pops up again identically when we look at electrical circuits.
This is the part about physical analogs, right? Finding connections between seemingly different areas of physics.
Precisely. Let's consider a simple electrical circuit containing a resistor R, an inductor L, and a capacitor C, all connected in series with an alternating voltage source VT. If you write down the equation that governs the amount of charge Q that has flowed past a point in that circuit,
using Kirchhoff's laws and the voltage-current relationships for R, L, and C.
right, you end up with an equation that looks like this. L times the second derivative of Q with respect to time plus R times the first derivative of Q plus 1 over C times Q equals the driving voltage V.
Hang on. LD/QQDT plus RD/QDT plus 1CQ plus 1CQ. That looks incredibly familiar.
It should. Compare it to the mechanical oscillator equation. MDON dxdt plus gammum dxdt plus kx is identical.
Wow. So there's a direct one-to-one mapping between the components.
A perfect analogy. The inductance, L, in the circuit plays exactly the same mathematical role as the mass M in the mechanical system. Both represent inertia resistance to change in motion or change in current.
Okay, L corresponds to M. What else?
The resistance R in the circuit corresponds directly to the frictional coefficient term, gammum, in mechanics. Both dissipate energy.
R is like friction. Got it.
The reciprocal of the capacitance, 1C, corresponds to the spring constant, K. Both relate to a restoring force, one electrical, one mechanical.
1C is like K.
Yeah.
And the variables themselves.
The charge Q that has flowed in the circuit is the analog of the displacement, X, of the mass, and the driving voltage, V, is the analog of the driving force, F.
That's amazing. So mass becomes inductance, friction becomes resistance, springiness becomes 1 over capacitance, displacement becomes charge, and force becomes voltage.
Exactly. It's a complete mathematical equivalence.
What's the big deal, though? Why is this analogy so important?
Well, think about the practical implications. It means if you have a really complicated mechanical problem, say, designing a sophisticated car suspension system with multiple springs and shock absorbers, which act like dampers, solving all the coupled differential equations directly might be incredibly difficult, especially back before powerful digital computers.
Okay.
But because the electrical analog equation is identical, you could instead build a relatively simple and cheap electrical circuit with corresponding values of inductors, resistors, and capacitors.
An RLC circuit that mimics the suspension.
Precisely. Then you could apply voltages that mimic the forces the suspension would experience, like hitting bumps, and simply measure the resulting charges or currents in the circuit using standard electrical instruments.
And those measured electrical quantities would directly tell you about the displacements and velocities in the mechanical system you were trying to design.
Exactly. This is the whole principle behind analog computers. You use one physical system, electrical, easy to build and measure, to simulate and solve problems in another physical system, mechanical, potentially complex, and hard to experiment with directly. Nature fundamentally doesn't care if the X represents meters or coulombs, as long as it obeys the same linear differential equation.
That really highlights the unifying power of the mathematics.
It does, and this principle of linearity also underpins all the standard techniques we use for analyzing more complex circuits, especially with alternating current, AC. This brings us to section 25-5, dealing with impedance.
Right, impedance. In AC circuits, we don't just talk about resistance, we talk about impedance, Z, which includes the effects of capacitors and inductors too. The relationship often looks like Ohm's law, V through Z times I, but Z can be a complex number.
Correct. Impedance generalizes the idea of resistance to AC circuits where phase shifts between voltage and current occur due to capacitors and inductors. But the key thing is how we combine these impedances when we build circuits.
And the rules for combining them depend on linearity, you're saying?
Absolutely. They flow directly from superposition and Kirchhoff's laws, which themselves rely on linearity. Consider components connected in series.
Okay, one after another, so the same current flows through all of them.
Right. And because voltages in a loop must add up, Kirchhoff's voltage law, based on linearity, the total voltage drop across the series combination is the sum of the individual voltage drops. If VZI for each, then V total V1 plus V2 plus Z1I plus Z2I, Z1 plus Z2I.
Ah, so the total impedance Z total is just Z1 plus Z2.
Yeah.
Impedances in series simply add up.
Just add them up. Simple consequence of linearity. Now, what about components in parallel?
Okay, connected side by side, so the voltage across each component is the same, but the total current splits between them.
Exactly. Here we use Kirchhoff's current law, also based on linearity. The total current flowing into the parallel combination must equal the sum of the currents flowing through each branch. I total equals I1 plus I2.
And since I equal VZ for each branch.
We get I total equals VZ1 plus VZ2, but we also know I total equals VZ total. So VZ total equals VZ1 plus VZ2.
And if we divide out the common voltage V, we get the rule for parallel impedances. 1 over Z total equals 1 over Z1 plus 1 over Z2.
The reciprocal rule, just like adding parallel resistors in DC circuits, again, a direct result of the underlying linearity of the circuit laws.
So even these fundamental rules of circuit analysis that we use all the time are really just extensions built upon those first two simple properties, additivity and homogeneity.
That's the core message of the chapter, I think. We started with just two seemingly simple algebraic properties that define linearity.
Additivity and homogeneity.
And from those two rules, we derived this incredibly rich and universal framework. It explains the structure of solutions to differential equations. It gives us the powerful principle of superposition. It clarifies why resonance happens and why radio tuning can be so sharp. And it reveals these profound analogies connecting mechanics and electricity.
The simplicity of the math is really what gives linear systems their immense predictive power.
It really is.
So wrapping this up, what's the main takeaway for someone studying physics? The real lesson of this chapter isn't just memorizing the formula for impedance or the damping equation, is it?
No, not at all. I think the deeper lesson is appreciating how the same mathematical structure can appear in vastly different physical contexts. Seeing that the equation for a swinging pendulum is fundamentally the same as the one for an RLC circuit that's powerful, it means understanding the math in one area instantly gives you insight into another. It unifies your understanding.
It breaks down the artificial walls between different subjects in physics.
Exactly. And maybe that leads to a final sort of provocative thought to leave people with. Given that so many of the fundamental laws of physics that we know, certainly classical electromagnetism governed by Maxwell's equations, and even quantum mechanics in its basic Schrödinger equation form are fundamentally linear.
Right.
When we look out at the universe and see incredibly complex, seemingly chaotic nonlinear behavior, things like turbulence in fluids, or the intricate dynamics of weather systems, or maybe even complex biological processes, is that complexity a sign that our fundamental linear descriptions are failing or incomplete?
Oh.
Or is it possible that we're simply witnessing the result of superposition applied to systems with an enormous number of degrees of freedom, driven by incredibly complex forces, but where the underlying interactions are still governed by those simple linear rules? Could the apparent nonlinearity just be complexity emerging from linear foundations?
That's a really interesting question. Is the messiness we see in nature a failure of linearity, or just linearity applied on a scale that's almost too complex for us to easily track? Something to definitely think about.
Definitely food for thought.
Well, that seems like a perfect place to end our deep dive into Feynman's take on the unifying power of linear systems in Chapter 25. Thanks for walking us through that.
My pleasure. It's a fantastic chapter.
And thank you for joining us. We hope this gives you a clearer picture of these crucial concepts. We'll catch you on the next deep dive.